In geometry and physics, spinors are elements of a vector space that can be associated with Euclidean space. Like geometric vectors and more general tensors, spinors transform linearly when the Euclidean space is subjected to a slight rotation. When a sequence of such small rotations is composed to form an overall final rotation, however, the resulting spinor transformation depends on which sequence of small rotations was used, unlike for vectors and tensors. A spinor transforms to its negative when the space is rotated through a complete turn from 0 a degree to 360 a degree, and it is this property that characterizes spinors. It is also possible to associate a substantially similar notion of spinor to Minkowski space, in which case the Lorentz transformations of special relativity play the role of rotations. Spinors were introduced in geometry by Élie Cartan in 1913. In the 1920s, physicists discovered that spinors are essential to describe the intrinsic angular momentum, or spin, of the electron and other subatomic particles. Spinors are characterized by the specific way in which they behave under rotations. They change in different ways depending not just on the overall final rotation, but the details of how that rotation was achieved. There are two topologically distinguishable classes of paths through rotations that result in the same overall rotation, as famously illustrated by the belt trick puzzle. These two inequivalent classes yield spinor transformations of opposite sign. The spin group is the group of all rotations keeping track of the class. It doubly covers the rotation group, since each rotation can be obtained in two inequivalent ways as the endpoint of a path. The space of spinors by definition is equipped with a linear representation of the spin group, meaning that elements of the spin group act as linear transformations on the space of spinors, in a way that genuinely depends on the homotopy class. Although spinors can be defined purely as elements of a representation space of the spin group, they are typically defined as elements of a vector space that carries a linear representation of the Clifford algebra. The Clifford algebra is an associative algebra that can be constructed from Euclidean space and its inner product in a basis-independent way. Both the spin group and its Lie algebra are embedded inside the Clifford algebra in a natural way, and in applications the Clifford algebra is often the easiest to work with. After choosing an orthonormal basis of Euclidean space, a representation of the Clifford algebra is generated by gamma matrices that satisfy a set of canonical anti-commutation relations. The spinors are the column vectors on which these matrices act. In three Euclidean dimensions, for instance, the Pauli spin matrices are a set of gamma matrices, and the two-component complex column vectors on which these matrices act are spinors. However, the particular matrix representation of the Clifford algebra, and hence what precisely constitutes a column vector, involves the choice of basis and gamma matrices in an essential way. As a representation of the spin group, this realization of spinors as column vectors will either be irreducible if the dimension is odd, or it will decompose into a pair of so-called half-spin, or well representations if the dimension is even. Introduction. What characterizes spinors and distinguishes them from geometric vectors and other tensors is subtle. Consider applying a rotation to the coordinates of a system. No object in the system itself has moved, only the coordinates have, so there will always be a compensating change in those coordinate values when applied to any object of the system. Geometrical vectors, for example, have components that will undergo the same rotation as the coordinates. More broadly, any tensor associated with a system also has coordinate descriptions that adjust to compensate for changes to the coordinate system itself. Spinors do not appear at this level of the description of a physical system, when one is concerned only with the properties of a single isolated rotation of the coordinates. Rather, spinors appear when we imagine that instead of a single rotation, the coordinate system is gradually rotated between some initial and final configuration. For any of the familiar and intuitive quantities associated with the system, the transformation law does not depend on the precise details of how the coordinates arrived at their final configuration. Spinors, on the other hand, are constructed in such a way that makes them sensitive to how the gradual rotation of the coordinates arrived there. They exhibit path dependence. It turns out that, For any final configuration of the coordinates, there are actually two inequivalent gradual rotations of the coordinate system that result in this same configuration. This ambiguity is called the homotopy class of the gradual rotation. The belt trick puzzle famously demonstrates two different rotations, one through an angle of 2i and the other through an angle of 4i, having the same final configurations but different classes. Spinors actually exhibit a sign reversal that genuinely depends on this homotopy class. This distinguishes them from vectors and other tensors, none of which can feel the class. Spinors can be exhibited as concrete objects using a choice of Cartesian coordinates. In 3 Euclidean dimensions, for instance, spinors can be constructed by making a choice of Pauli spin matrices corresponding to the 3 coordinate axes. These are 2A, 2 matrices with complex entries, and the 2-component complex column vectors on which these matrices act by matrix multiplication are the spinors. In this case, the spin group is isomorphic to the group of 2A, 2 unitary matrices with determinant 1, which naturally sits inside the matrix algebra. This group acts by conjugation on the real vector space spanned by the Pauli matrices themselves, realizing it as a group of rotations among them, but it also acts on the column vectors. More generally, a Clifford algebra can be constructed from any vector space V equipped with a quadratic form, such as Euclidean space with its standard dot product or Minkowski space with its standard Lorentz metric. Given a suitably normalized basis of V, the Clifford algebra is generated by gamma matrices, matrices that satisfy a set of canonical anti-commutation relations, and the space of spinors is the space of column vectors with components on which those matrices act. Although the Clifford algebra can be defined abstractly in a coordinate-independent way, its particular realization as a specific algebra of matrices depends on which orthogonal axes the gamma matrices represent. So what precisely constitutes a column vector also depends on such arbitrary choices. The orthogonal Lie algebra and the spin group associated to the quadratic form are both contained in the Clifford algebra, so every Clifford algebra representation also defines a representation of the Lie algebra and the spin group. Depending on the dimension and metric signature, this realization of spinors as column vectors may be irreducible or it may decompose into a pair of so-called half-spin, or well representations. Overview: there are essentially two frameworks for viewing the notion of a spinor. One is representation theoretic. In this point of view, one knows beforehand that there are some representations of the Lie algebra of the orthogonal group that cannot be formed by the usual tensor constructions. These missing representations are then labeled the spin representations, and their constituent spinors. In this view, a spinor must belong to a representation of the double cover of the rotation group SO, N, R, or more generally of double cover of the generalized special orthogonal group SO plus, P, Q, R, on spaces with metric signature. These double covers are Lie groups, called the spin group spin, N, or spin, P, Q. All the properties of spinors, and their applications and derived objects, are manifested first in the spin group. Representations of the double covers of these groups yield projective representations of the groups themselves, which do not meet the full definition of a representation. The other point of view is geometrical. One can explicitly construct the spinors, and then examine how they behave under the action of the relevant Lie groups. This latter approach has the advantage of providing a concrete and elementary description of what a spinor is. However, such a description becomes unwieldy when complicated properties of spinors, such as Fierz identities, are needed. Clifford algebras equals. The language of Clifford algebras provides a complete picture of the spin representations of all the spin groups, and the various relationships between those representations, via the classification of Clifford algebras. It largely removes the need for ad hoc constructions. In detail, let V be a finite-dimensional complex vector space with non-degenerate bilinear form G. The Clifford algebra Car, V, G, is the algebra generated by V along with the anti-commutation relation xy plus x equals 2G, x, y. it is an abstract version of the algebra generated by the gamma or Pauli matrices. If V equals Cn, with the standard form G, x, a euro y, equals xt y equals x1 y1 plus x and yn, we denote the Clifford algebra by Kn, C. Since by the choice of an orthonormal basis every complex vector space with non-degenerate form is isomorphic to this standard example, this notation is abused more generally if dim C, V, equals n. If n equals 2k is even, Kn, C, is isomorphic as an algebra to the algebra mat, 2k, a euro C, of 2k euro a euro 2k complex matrices. If n equals 2k euro plus a euro 1 is odd, car 2k plus 1, C, is isomorphic to the algebra mat, 2k, a euro C, a euro a euro mat, 2k, a euro C, of 2 copies of the 2k euro a euro 2k complex matrices. Therefore, in either case car, V, a euro G, has a unique irreducible representation, commonly denoted by I, of dimension 2, n/2. Since the Lie algebra so, V, a euro G, is embedded as a Lie subalgebra in car, V, a euro G, equipped with a Clifford algebra commutator as Lie bracket, the space I is also a Lie algebra representation of so, V, a euro G, called a spin representation. If n is odd, this Lie algebra representation is irreducible. If n is even, it splits further into two irreducible representations I equals I plus a euro a euro a called the well or half spin representations. Irreducible representations over the reals in the case when V is a real vector space are much more intricate, and the reader is referred to the Clifford algebra article for more details. Spin groups equals. Spinors form a vector space, usually over the complex numbers, equipped with a linear group representation of the spin group that does not factor through a representation of the group of rotations. The spin group is the group of rotations keeping track of the homotopy class. Spinors are needed to encode basic information about the topology of the group of rotations because that group is not simply connected, but the simply connected spin group is its double cover. So for every rotation there are two elements of the spin group that represent it. Geometric vectors and other tensors cannot feel the difference between these two elements, but they produce opposite signs when they affect any spinor under the representation. Thinking of the elements of the spin group as homotopy classes of one-parameter families of rotations, each rotation is represented by two distinct homotopy classes of paths to the identity. If a one-parameter family of rotations is visualized as a ribbon in space, with the arc length parameter of that ribbon being the parameter, then these two distinct homotopy classes are visualized in the two states of the belt trick puzzle. The space of spinors is an auxiliary vector space that can be constructed explicitly in coordinates, but ultimately only exists up to isomorphism in that there is no natural construction of them that does not rely on arbitrary choices such as coordinate systems. A notion of spinors can be associated, as such an auxiliary mathematical object, with any vector space equipped with a quadratic form such as Euclidean space with its standard dot product, or Minkowski space with its Lorentz metric. In the latter case, the rotations include the Lorentz boosts, but otherwise the theory is substantially similar. Terminology in physics equals, the most typical type of spinor, the Dirac Spinor, is an element of the fundamental representation of car P plus Q, C, the complexification of the Clifford algebra car P, a euro Q, R, into which the spin group spin, P, a euro Q, may be embedded. On a 2K or 2K plus one-dimensional space a Dirac spinor may be represented as a vector of 2K complex numbers. In even dimensions, this representation is reducible when taken as a representation of spin, P, a euro Q, and may be decomposed into two, the left-handed and right-handed well spinor representations. In addition, sometimes the non-complexified version of car P, Q, R, has a smaller real representation, the Majorana spinor representation. If this happens in an even dimension, the Majorana spinor representation will sometimes decompose into two Majorana euro well spinor representations. Dirac and well spinors are complex representations while Majorana spinors are real representations. The Dirac, Lorentz, well, and Majorana spinors are interrelated, and their relation can be elucidated on the basis of real geometric algebra. Massive particles, such as electrons, are described as Dirac spinors. The classical neutrino of the Standard Model of particle physics is an example of a well spinor. However, because of observed neutrino oscillation, it is now believed that they are not well spinors, but perhaps instead Majorana spinors. It is not known whether well spinors exist in nature. In 2015, an international team led by Princeton University scientists announced that they had found a quasi-particle that behaves as a well fermion. Spinors in representation theory . One major mathematical application of the construction of spinors is to make possible the explicit construction of linear representations of the Lie algebras of the special orthogonal groups, and consequently spinor representations of the groups themselves. At a more profound level, spinors have been found to be at the heart of approaches to the Atiyah-Singer index theorem, and to provide constructions in particular for discrete series representations of semisimple groups. The spin representations of the special orthogonal Lie algebras are distinguished from the tensor representations given by Wells' construction by the weights. Whereas the weights of the tensor representations are integer linear combinations of the roots of the Lie algebra, those of the spin representations are half-integer linear combinations thereof. Explicit details can be found in the spin representation article. Attempts at intuitive understanding . The spinor can be described, in simple terms, as a OE vectors of a space the transformations of which are related in a particular way to rotations in physical spatia . Stated differently, spinors, provide a linear representation of the group of rotations in a space with any number of dimensions, each spinor having components where or. Several ways of illustrating everyday analogies have been formulated in terms of the plate trick, tensoroids and other examples of orientation entanglement. Nonetheless, the concept is generally considered notoriously difficult to understand, as illustrated by Michael Atiyah's statement that is recounted by Dirac's biographer Graham Farmer. No one fully understands spinors. Their algebra is formally understood but their general significance is mysterious. In some sense they describe the OE square root of geometry and, just as understanding the square root of a 1 took centuries, the same might be true of spinors. History. The most general mathematical form of spinors was discovered by Élie Cartan in 1913. The word spinor was coined by Paul Ehrenfest in his work on quantum physics. Spinors were first applied to mathematical physics by Wolfgang Pauli in 1927, when he introduced his spin matrices. The following year, Paul Dirac discovered the fully relativistic theory of electron spin by showing the connection between spinors and the Lorentz group. By the 1930s, Dirac, Piet Hein and others at the Niels Bohr Institute created toys such as tensoroids to teach and model the calculus of spinors. Spinor spaces were represented as left ideals of a matrix algebra in 1930, by G. Jovet and by Fritz Soter. More specifically, instead of representing spinors as complex-valued 2D column vectors as Pauli had done, they represented them as complex-valued 2 A2 matrices in which only the elements of the left column are non-zero. In this manner the spinor space became a minimal left ideal in Mat. 2, C. In 1947 Marcel Rice constructed spinor spaces as elements of a minimal left ideal of Clifford algebras. Indiana, 1966/1967, David Hessens replaced spinor spaces by the even subalgebra Car1, 3, R, of the space-time algebra Car1, 3, R. As of the 1980s, the theoretical physics group at Birkbeck College around David Bohm and Basil Hiley has been developing algebraic approaches to quantum theory that build on Soter and Rice identification of spinors with minimal left ideals. Examples. Some simple examples of spinors in low dimensions arise from considering the even-graded subalgebras of the Clifford algebra Car-P, Q, R. This is an algebra built up from an orthonormal basis of n equals par Euro plus Q mutually orthogonal vectors under addition and multiplication, P of which have norm +1 and Q of which have norm +1, with the product rule for the basis vectors. Equals 2 dimensions equals, the Clifford algebra Car2, 0, R, is built up from a basis of one unit scalar, 1, 2 orthogonal unit vectors, I1 florin and I2 florins, and one unit pseudoscalar I equals I1 florin I2 florins. From the definitions above, it is evident that 2 equals 2 equals 1, and I1 florin I2 florins, equals AI1 florin I1 florin I2 florins I2 florins equals a 1. The even subalgebra Car2, 0, R, spanned by even-graded basis elements of Car2, 0, R, determines the space of spinors via its representations. It is made up of real linear combinations of 1 and I1 florin I2 florins. As a real algebra, Car2, 0, R, is isomorphic to field of complex numbers C. As a result, it admits a conjugation operation, sometimes called the reverse of a Clifford element, defined by which, by the Clifford relations, can be written. The action of an even Clifford element I cubed to Car2, 0, R, on vectors, regarded as one-graded elements of Car2, 0, R, is determined by mapping a general vector U equals A1 I1 florin plus A2 I2 florins to the vector, where I cubed A, is the conjugate of I cubed, and the product is Clifford multiplication. In this situation, a spinor is an ordinary complex number. The action of I cubed on a spinor I is given by ordinary complex multiplication. An important feature of this definition is the distinction between ordinary vectors and spinors, manifested in how the even-graded elements act on each of them in different ways. In general, a quick check of the Clifford relations reveals that even-graded elements conjugate commute with ordinary vectors. On the other hand, comparing with the action on spinors I cubed, I, A euro equals a euro I cubed I cubed on ordinary vectors acts as the square of its action on spinors. Consider, for example, the implication this has for plane rotations. Rotating a vector through an angle of I corresponds to I cubed 2 equals exp, I A euro I1 florin I2 florins, so that the corresponding action on spinors is via I cubed equals a plus or minus a euro exp, I A euro I1 florin I2 florins /2. In general, because of logarithmic branching, it is impossible to choose a sign in a consistent way. Thus the representation of plane rotations on spinors is two-valued. In applications of spinors in two dimensions, it is common to exploit the fact that the algebra of even-graded elements is identical to the space of spinors. So, by abuse of language, the two are often conflated. One may then talk about the action of a spinor on a vector. In a general setting, such statements are meaningless. But in dimensions 2 and 3 they make sense. Examples: the even-graded element corresponds to a vector rotation of 90 degree from I1 florin around towards I2 florins, which can be checked by confirming that it corresponds to a spinor rotation of only 45 degree, however. Similarly, the even-graded element I cubed a euro equals a euro AI1 florin I2 florins corresponds to a vector rotation of 180 degree, but a spinor rotation of only 90 degree. Continuing on further, the even-graded element I cubed a euro equals a euro A1 corresponds to a vector rotation of 360 degree, but a spinor rotation of 180 degree. Equals 3 dimensions equals, main articles spinors in 3 dimensions, quaternions and spatial rotation. The Clifford algebra Car3, 0, R, is built up from a basis of one unit scalar, 1, 3 orthogonal unit vectors, I1 florin, I2 florins and I3 florins, the 3 unit bivectors I1 florin I2 florins, I2 florins I3 florins, I3 florins I1 florin and the pseudoscalar I equals I1 florin I2 florins I3 florins. It is straightforward to show that 2 equals 2 equals 2 equals 1, and 2 equals 2 equals 2 equals 2 equals a 1. The subalgebra of even-graded elements is made up of scalar dilations and vector rotations, where corresponds to a vector rotation through an angle I about an axis defined by a unit vector v equals a1 I1 florin a euro plus a euro a2 I2 florins a euro plus a euro a3 I3 florins. As a special case, it is easy to see that, if v equals I3 florins, this reproduces the I1 florin I2 florins rotation considered in the previous section. And that such rotation leaves the coefficients of vectors in the I3 florins direction invariant, since the bivectors I2 florins I3 florins, I3 florins I1 florin and I1 florin I2 florins are in fact Hamilton's quaternions I, J and K, discovered in 1843. With the identification of the even-graded elements with the algebra H of quaternions, as in the case of two dimensions, the only representation of the algebra of even-graded elements is on itself. Thus the spinors in three dimensions are quaternions, and the action of an even-graded element on a spinor is given by ordinary quaternionic multiplication. Note that the expression for a vector rotation through an angle I, the angle appearing in I cubed, was halved. Thus the spinor rotation I cubed, I, a euro equals a euro I cubed. I will rotate the spinor I through an angle 1/2 the measure of the angle of the corresponding vector rotation. Once again, the problem of lifting a vector rotation to a spinor rotation is two-valued. The expression within place of I/2 will produce the same vector rotation, but the negative of the spinor rotation. The spinor quaternion representation of rotations in 3D is becoming increasingly prevalent in computer geometry and other applications, because of the notable brevity of the corresponding spin matrix, and the simplicity with which they can be multiplied together to calculate the combined effect of successive rotations about different axes. Explicit constructions. A space of spinors can be constructed explicitly with concrete and abstract constructions. The equivalence of these constructions are a consequence of the uniqueness of the spinor representation of the complex Clifford algebra. For a complete example in dimension 3, see spinors in 3 dimensions. Component spinors equals, given a vector space V and a quadratic form G in explicit matrix representation of the Clifford algebra car, B, a euro G, can be defined as follows. Choose an orthonormal basis E1 a euro n for V, that is G, A1/4 A1/2 equals I1/4 I1/2, where I1/4 I1/4 equals A plus or minus 1 and I1/4 I1/2 equals 0 for I1/4 a per mil I1/2. Let K equals a euro n/2 a euro or. Fix a set of 2 car euro a euro 2k matrices I cubed 1 a euro I cubed n such that I cubed I1/4 I cubed I1/2 plus I cubed I1/2 I cubed I1/4 equals 2 I1/4 I1/2 1. Then the assignment A1/4 A I cubed I1/4 extends uniquely to an algebra homomorphism car, B, a euro G, a mat, 2k, a euro C, by sending the monomial A1/4 1 a euro A1/4 k in the Clifford algebra to the product I cubed I1/4 1 a euro I cubed I1/4 k of matrices and extending linearly. The space I equals C2k on which the gamma matrices act is now a space of spinors. One needs to construct such matrices explicitly, however. In dimension 3, defining the gamma matrices to be the Pauli sigma matrices gives rise to the familiar two-component spinors used in non-relativistic quantum mechanics. Likewise, using the 4 Dirac gamma matrices gives rise to the four-component Dirac spinors used in 3+1-dimensional relativistic quantum field theory. In general, in order to define gamma matrices of the required kind, one can use the Wheeler-Euro-Brouwer matrices. In this construction, the representation of the Clifford algebra car, B, a euro G, the Lie algebra SO, B, a euro G, and the spin group spin, B, a euro G, all depend on the choice of the orthonormal basis and the choice of the gamma matrices. This can cause confusion over conventions, but invariants like traces are independent of choices. In particular, all physically observable quantities must be independent of such choices. In this construction, a spinor can be represented as a vector of 2k complex numbers and is denoted with spinor indices. In the physics literature, Abstract spinor indices are often used to denote spinors even when an abstract spinor construction is used. Abstract spinors equals, there are at least two different, but essentially equivalent, ways to define spinors abstractly. One approach seeks to identify the minimal ideals for the left action of car, B, G, on itself. These are subspaces of the Clifford algebra of the form car, B, G, I per mil, admitting the evident action of car, B, G, by left multiplication, car euros I per mil or Cx I per mil. There are two variations on this theme. One can either find a primitive element I per mil that is a nilpotent element of the Clifford algebra, or one that is an idempotent. The construction via nilpotent elements is more fundamental in the sense that an idempotent may then be produced from it. In this way, the spinor representations are identified with certain subspaces of the Clifford algebra itself. The second approach is to construct a vector space using a distinguished subspace of V, and then specify the action of the Clifford algebra externally to that vector space. In either approach, the fundamental notion is that of an isotropic subspace W. Each construction depends on an initial freedom in choosing this subspace. In physical terms, this corresponds to the fact that there is no measurement protocol that can specify a basis of the spin space, even if a preferred basis of V is given. As above, we let B an n-dimensional complex vector space equipped with a non-degenerate bilinear form. If V is a real vector space, then we replace V by its complexification var euro ash, ra euro c, and let G denote the induced bilinear form on var euro ash, ra euro c. Let W be a maximal isotropic subspace, that is a maximal subspace of V such that GW equals a euro 0. If n equals a euro 2k is even, then let W be an isotropic subspace complementary to W. If n equals a euro 2k plus 1 is odd, let W be a maximal isotropic subspace with W of V euro W equals 0, and let U be the orthogonal complement of W euro ash a euro 1. In both the even and odd-dimensional cases W and W have dimension k. In the odd-dimensional case, U is one-dimensional, spanned by a unit vector U. Equals minimal ideals equals, since W euro squared is isotropic, multiplication of elements of W euro squared inside car, B, a euro G, is skew. Hence vectors in W euro squared anti-commute, and car, W euro squared, a euro G W euro squared equals car, W euro squared, 0, is just the exterior algebra in W euro squared. Consequently, the k-fold product of W euro squared with itself, W euro squared k, is one-dimensional. Let I per mil be a generator of W euro squared k. In terms of a basis W euro squared 1. W euro squared k of n W euro squared, one possibility is to set. Note that I per mil 2 equals 0, and moreover, W euro squared I per mil equals 0 for all W euro squared or W euro squared. The following facts can be proven easily: if n equals 2k, then the left ideal I equals car, B, a euro G, I per mil is a minimal left ideal. Furthermore, this splits into the two spin spaces I plus equals car even E per mil and IA equals car D per mil on restriction to the action of the even Clifford algebra. If n equals 2k plus 1, then the action of the unit vector U on the left ideal car, B, a euro G, I per mil decomposes the space into a pair of isomorphic irreducible eigenspaces, corresponding to the respective eigenvalues plus 1 and a 1. In detail, suppose for instance that n is even. Suppose that I is a non-zero left ideal contained in car, B, a euro G, I per mil. We shall show that I must be equal to car, B, a euro G, I per mil by proving that it contains a non-zero scalar multiple of I per mil. Fix a basis V of W and a complementary basis E a euro squared of W euro squared so that V which a euro squared plus W j a euro squared V equals I ish, and V, 2 equals 0, 2 equals 0. Note that any element of I must have the form I plus or minus I per mil, by virtue of our assumption that I car, B, a euro G, a euro I per mil. Let I plus or minus I per mil I be any such element. Using the chosen basis, we may write where the I1 are Euro-IP are scalars, and the Bj are auxiliary elements of the Clifford algebra. Observe now that the product. Pick any non-zero monomial A in the expansion of I plus or minus with maximal homogeneous degree in the elements we, then, is a non-zero scalar multiple of I per mil, as required. Note that for n even, this computation also shows that as a vector space. In the last equality we again used that W is isotropic. In physics terms, this shows that I is built up like a Fock space by creating spinors using anti-commuting creation operators and W acting on a vacuum I per mil. Exterior algebra construction equals, the computations with the minimal ideal construction suggest that a spinor representation can also be defined directly using the exterior algebra in W equals j W of the isotropic subspace W. Let I equals it, W denote the exterior algebra of W considered as vector space only. This will be the spin representation, and its elements will be referred to as spinors. The action of the Clifford algebra on I is defined first by giving the action of an element of V on I, and then showing that this action respects the Clifford relation and so extends to a homomorphism of the full Clifford algebra into the endomorphism ring end, I by the universal property of Clifford algebras. The details differ slightly according to whether the dimension of V is even or odd. When dim, V, is even, V equals W y euro squared where y euro squared is the chosen isotropic complement. Hence any V of V decomposes uniquely as V equals W plus y euro squared with W a W and y euro squared a y euro squared. The action of V on a spinor is given by where I, y euro squared is interior product with y euro squared using the non-degenerate quadratic form to identify V with var, and I micron, W, denotes the exterior product. It may be verified that C, U, C, V, plus C, V, C, U, equals 2G, U, V, and so C respects the Clifford relations and extends to a homomorphism from the Clifford algebra to end, I. The spin representation I further decomposes into a pair of irreducible complex representations of the spin group via when dim, V, is odd, V equals W U y euro squared, where U is spanned by a unit vector U orthogonal to W. The Clifford action C is defined as before on W y euro squared, while the Clifford action of U is defined by as before. One verifies that C respects the Clifford relations, and so induces a homomorphism. Hermitian vector spaces and spinors equals, if the vector space V has extra structure that provides a decomposition of its complexification into two maximal isotropic subspaces, then the definition of spinors becomes natural. The main example is the case that the real vector space V is a Hermitian vector space, that is, V is equipped with a complex structure J that is an orthogonal transformation with respect to the inner product G on V. Then var euro ra euro C splits in the A plus or minus I eigenspaces of J. These eigenspaces are isotropic for the complexification of G and can be identified with a complex vector space and its complex conjugate. Therefore, for a Hermitian vector space the vector space CV is a spinor space for the underlying real Euclidean vector space. With the Clifford action as above but with contraction using the Hermitian form, this construction gives a spinor space at every point of an almost Hermitian manifold and is the reason why every almost complex manifold has a Spinx structure. Likewise, every complex vector bundle on a manifold carries a Spinx structure. Kleber-Gordon decomposition. A number of Kleber-Gordon decompositions are possible on the tensor product of one spin representation with another. These decompositions express the tensor product in terms of the alternating representations of the orthogonal group. For the real or complex case, the alternating representations are equals of the representation of the orthogonal group on skewed tensors of rank R. In addition, for the real orthogonal groups, there are three characters, I florin plus a euro O, P, a euro Q, AA1, a euro plus 1 given by I florin plus, R, equals a 1, if A reverses the spatial orientation of E, plus 1, if A preserves the spatial orientation of E. I florin A euro O, P, a euro Q, AA1, a euro plus 1 given by I florin A, R, equals a 1, if A reverses the temporal orientation of E, plus 1, if A preserves the temporal orientation of E, I. Florin equals I florin plus I florin A euro. The Kleber-Gordon decomposition allows one to define, among other things, an action of spinors on vectors. A Hermitian metric on the complex representations of the real spin groups. A Dirac operator on each spin representation. Equals even dimensions equals, if na euro equals a euro 2k is even, then the tensor product of I with the contragradient representation decomposes as, which can be seen explicitly by considering the action of the Clifford algebra on decomposable elements I plus or minus I per mil a euro ash, a euro I squared I per mil a euro squared. The rightmost formulation follows from the transformation properties of the Hodge-Star operator. Note that on restriction to the even Clifford algebra, the paired summands IP ash I florin IP are isomorphic, but under the full Clifford algebra they are not. There is a natural identification of I with its contragradient representation via the conjugation in the Clifford algebra. So I a euro ash, a euro I also decomposes in the above manner. Furthermore, under the even Clifford algebra, the half-spin representations decompose. For the complex representations of the real Clifford algebras, the associated reality structure on the complex Clifford algebra descends to the space of spinors. In this way, we obtain the complex conjugate I of the representation I, and the following isomorphism is seen to hold. In particular, note that the representation I of the orthogonal spin group is a unitary representation. In general, there are Kleber-Gordon decompositions. In metric signature, the following isomorphisms hold for the conjugate half-spin representations: if Q is even, then and; if Q is odd, then and. Using these isomorphisms, one can deduce analogous decompositions for the tensor products of the half-spin representations IA plus or minus ash, IA plus or minus. Equals odd dimensions equals, if na euro equals a euro 2k plus 1 is odd, then. In the real case, once again the isomorphism holds. Hence there is a Kleber-Gordon decomposition given by equals consequences equals. There are many far-reaching consequences of the Kleber-Gordon decompositions of the spinor spaces. The most fundamental of these pertain to Dirac's theory of the electron, among whose basic requirements are, a manner of regarding the product of two spinors II as a scalar. In physical terms, a spinor should determine a probability amplitude for the quantum state. A manner of regarding the product II as a vector. This is an essential feature of Dirac's theory, which ties the spinor formalism to the geometry of physical space. A manner of regarding a spinor is acting upon a vector, by an expression such as IV. In physical terms, this represents an electric current of Maxwell's electromagnetic theory, or more generally a probability current. Summary in low dimensions: in one dimension, the single spinor representation is formally major honor, a real one-dimensional representation that does not transform. In two Euclidean dimensions, the left-handed and the right-handed well spinor are one-component complex representations, that is complex numbers that get multiplied by a plus or minus e/2 under a rotation by angle I. In three Euclidean dimensions, the single spinor representation is two-dimensional and quaternionic. The existence of spinors in three dimensions follows from the isomorphism of the groups SU, 2, a per mil spin, 3, that allows us to define the action of spin, 3, on a complex two-component column. The generators of SU, 2, can be written as Pauli matrices. In four Euclidean dimensions, the corresponding isomorphism is spin, 4, a per mil SU, 2, a euro A euro SU, 2. There are two inequivalent quaternionic two-component well spinors and each of them transforms under one of the SU, 2, factors only. In five Euclidean dimensions, the relevant isomorphism is spin, 5, a per mil USP, 4, a per mil SP, 2, that implies that the single spinor representation is four-dimensional and quaternionic. In six Euclidean dimensions, The isomorphism spin, 6, a permel SU, 4, guarantees that there are two four-dimensional complex well representations that are complex conjugates of one another. In 7 Euclidean dimensions, the single spinor representation is 8-dimensional and real. No isomorphisms to a Lie algebra from another series exist from this dimension on. In 8 Euclidean dimensions, there are two Wheeler-Euro-Majorana real 8-dimensional representations that are related to the 8-dimensional real vector representation by a special property of spin, 8, called triality. In Euro plus a Euro 8 dimensions, the number of distinct irreducible spinor representations and their reality mimics the structure in D dimensions, but their dimensions are 16 times larger. This allows one to understand all remaining cases. See Bott periodicity. In spacetimes with p-spatial and q-time-like directions, the dimensions viewed as dimensions over the complex numbers coincide with the case of the dimensional Euclidean space, but the reality projections mimic the structure in Euro-A-Q Euclidean dimensions. For example, in 3 a Euro plus a Euro 1 dimensions there are two non-equivalent well-complex two-component spinors, which follows from the isomorphism SL, 2, a Euro C, a permel spin, 3, 1. See also, Anion, Dirac equation in the algebra of physical space, Einstein Elie Cartan theory, pure spinor, spinor 1/2, spinor bundle, supercharge, twistor theory. Notes. References. Further reading, Brauer, Richard. Well, Herman, Spinors in N Dimensions, American Journal of Mathematics 57, 425 a Euro 449, doi, 10.230/2371218, JSTOR 2371218. Cartan, a permel Lie, les groupes projectifs qui ne l'émergent invarianti aucune multiplicité copyright plain, Bull. Soc. Math. France 41, 53 a Euro 96. Cartan, a permel Lie, The Theory of Spinors, Paris, Herman, ISBN 978-0-486-64070-9, Chevalier, Claude, The Algebraic Theory of Spinors and Clifford Algebras, Columbia University Press, ISBN 978-3-540-57063-9. Dirac, Paul M., The Quantum Theory of the Electron, Proceedings of the Royal Society of London A117, 610 a Euro 624, JSTOR 94981. Fulton, William. Harris, Joe, Representation Theory. A First Course, Graduate Texts in Mathematics, Readings in Mathematics 129, New York, Springer Verlag, ISBN 0-387-97495-4, Mr. 1153249. Gilkey, Peter B., Invariance Theory, The Heat Equation, and the Atiyah-Singer Index Theorem, Publish or Perish, ISBN 0-914098-20-9. Harvey, F. Rees, Spinors and Calibrations, Academic Press, ISBN 978-0-12-329650-4. Haswinkel, Michiel, ed., Spinor, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, Hitchin, Nigel J., Harmonic Spinors, Advances in Mathematics 14, 1 a Euro 55, doi, 10.1016/0001-8708, 74, 90021-8, Mr. 358873. Lawson, H. Blaine. Michelson, Marie-Louise, Spin Geometry, Princeton University Press, ISBN 0-691-08542-0. Pauli, Wolfgang, Zur Quantenmechanik des Mantischen Elektrons, Zeitschrift Fahr 1/4 of Physik 43, 601 a Euro 632, bibcode, 1927 ZPHY. 43601p, doi, 10.1007/BF013973226. Penrose, Roger. Rinner, W. Spinors and Spartier Eurotime, Volume 2, Spinor and Twistor Methods in Spartier Eurotime Geometry, Cambridge University Press, ISBN 0-521-34786-6. Tomonaga, Shinichiro, Lecture 7, The Quantity Which Is Neither Vector Nor Tensor, The Story of Spin, University of Chicago Press, pages 129, ISBN 0-226-80794-0.